So let's start right off with our first paper. It's titled Initial Work on Development of an Open Streaming Media Standard for Field of Light Displays, with a very nice acronym. The speaker is Mr. Stephen Kelley of Third Dimension Technologies.
Good morning. My name is Steve Kelley, and my talk today is on the initial work we've done on the development of a streaming standard for field of light displays. The primary author on this paper was Jamison Daniel, but he couldn't be here today, so I'm filling in for him. So this project is sponsored by the Air Force, the Research Lab in Dayton, Ohio. The program facilitators are Third Dimension Technologies, Oak Ridge National Lab, and Insight Media. So why do we need a standard for streaming data to fold devices? Well, 3D data are increasing dramatically. There's lots of new sensors. Sensors are being used for different things, and you can have 3D models that are either actual or computer generated. And we know that when you can work with your data in 3D, that it improves productivity. Stereo 3D is generally not acceptable for working with these data sets that make a lot of people sick. You've got divergence and accommodation problems and various other shortcomings with stereo 3D. So a field of light display is desired. However, the lack of a standard for providing data to these displays is slowing down the development and the adoption of these types of displays. Now, there have been some commercial bodies that are working on standards, but they're mostly focused on stereo 3D and 2D. So we need a common model so that people can write an application that'll run on all these displays. Now, this is an example of what might be a field of light display. So the field of light display reproduces all the light that you would get from a real-world object. So you have no divergence and accommodation mismatch. You don't need glasses. You don't need the headgear. And the fact that you have stereopsis and motion parallax gives you a better understanding of the data that you're looking at. So here's a use case example where you have data coming from a variety of sources going into an application. The application is assembling this data and making a 3D representation. Well, it'd be nice to have that on a display where you can, just by moving left and right, you can look around objects, or you can have several people looking at the same scene, and each one is looking at it from a different perspective. So Third Dimension Technologies, we are a developer of fold systems. We've had many years of experience with the challenges doing multi-view rendering. Our current projects, we delivered an F-35 flight simulator to the Air Force, and we're working on this standard currently. Uh-oh. Oh, there it goes. Sorry. My wife said I should do something to make this, to keep people awake. Maybe that was it there. So there are a lot of problems with fold systems. They must render the scene from multiple viewpoints. You can't just have two. So that means that fold systems generally generate gigapixels, which ends up being far too much data to transmit. And not only that, but if you're transmitting pixel data, then the application would have to know how that data needs to be represented on the target display. And so that would tie the application to that display. Fold systems also, we're going to need to have access to shaders. So that means that the source application is going to have to include stuff that a display will be able to use. And typical applications provide only one viewpoint. So our objectives are to create a display agnostic streaming standard. And by display agnostic, we mean that you should be able to consume this stream with a standard 2D display, a stereo 3D, or a fold system. The standard will include the scene description transmission format, and it'll allow for some point of view and flow control. We want the standard to be an open international standard. We also want it to support the needs of industry and DoD. And we want it to be supported by display and application developers. And if we can get them to buy in, there will be more applications that can run on fold systems. So our approach was to start simple. We want to use OpenGL for the SMFoLD interface. So the source application would link to an SMFoLD library, and that would replace the OpenGL library. So the SMFoLD library exports the OpenGL functions. The display applications would include all of the definitions in the standard so that the display application could unwind what the application did. We're going to limit display types to mesh and textures, so you're sending geometry instead of pixels. It reduces the bandwidth requirements considerably. And for the shaders, the source application will have to include these named variables that are called uniforms in OpenGL, and those variables will give the display application access to what it needs to render as it needs to. So here's the flow model. You've got a source application, it's linked to the SMFoLD source process library. So when the application launches, it'll call into the SMFoLD DLL. The SMFoLD DLL will encode it and send it over the network. The display process, which is sitting there listening for incoming data, will pull the data in and decompress and decrypt it as necessary and write it to a buffer. When the frame is complete, it fires an event that the display application is listening for, and then it'll read the memory out of the buffer and render it. And the display application would be display specific, and so it would know how it needed to do the rendering. So what do we mean by an SMFoLD frame? An SMFoLD frame is simply the collection of all the data that is required to generate a 3D scene. So you will have values that represent function calls. You've got data that are the argument list for those functions. And then there are some metadata that we will have to generate so that the displays will have the information that they need. And you can define discrete objects using meshes and download those, and they can reside on the card so that the first frame may be fairly large, but subsequent frames can be quite small because it may be that all you need to do is send new transformation information for the next frame. So this is the data format. You've got a viewpoint, you have function code, the length of the data, followed by the data. At the end of the data for that function, there's another function code, there's the data length and the data for the function, and so on until the end of the frame is reached. So again, you have the source application processing 3D data. It calls into the source process API, which again is OpenGL with a couple of extensions. The source process will encode the functions and the arguments and write all that to a memory buffer. At the end of the frame, the buffer will be compressed and encrypted as needed, and then output to the network. On the display side, the frame comes in, gets decompressed and decrypted, and that puts it back into the same form it was in that the application put it in. And so that is restored to opcodes and data. And then those opcodes and data are written into a memory buffer that the display application also has access to. So then the display application would perform the multi-view rendering as it needs. And then we have the metadata that is used to set display-specific parameters, and the shaders contain the hooks to utilize those parameters. So, the graphics pipeline is implemented in shaders, and more programs are going to more shader-based programming. And that presents some challenges. So we know that the vertex shader performs the geometric transformations and turns your user data into normalized device coordinates. At that point, you can do some simple trig and convert or adjust the geometry for a specific eye point. So you can take a central view, and by having this geometric function that we are defining, you require that it be called from the vertex shader or any other point where a vertex is converted into normalized device coordinates. And then you can call this function. It'll do the geometry correction for the particular viewpoint. So in conclusion, we believe that using OpenGL, which is a well-known, well-understood API, to provide the graphics primitives, plus, again, a few extensions, that this will provide a very short, quick path to getting to an open standard. We think that we can get very high frame rates over existing networks by utilizing the GPU memory and using buffered objects, et cetera, display lists and those sorts of things. And as the standard matures, then different data types can be added, different features can be added. We need support of application and display system providers. We need buy-in from the industry. And our next steps, we are in the process of implementing our idea for a streaming standard, and we will be making our results public. And when we get permission, we're going to share our implementation of the source process, the source application, the display process, and the display application. We're going to make all that available as open source. We want to find applications and display developers who will work with us to implement the standard on their system, provide additional testing, et cetera. Now, we have had 2 SMFoLD workshops. We're going to be having a third. The time and place has not yet been announced, but we would certainly invite you to visit smfold.org on a regular basis to look for or watch for the announcement of this third workshop. And ultimately, what we want to do is find a home for this standard with an existing standards body, such as, say, MPEG, for example. So we want to get it to the point where some established standards body will take it over. And with that, are there any questions?